welcome to the last part of our Chapter 2 lecture video discussion. Previously, we looked at in section 2.1, we looked at how we can summarize categorical data using frequency distribution table, bar chart, and pie chart. We also looked at how a dot plot can be used to summarize and present categorical data. In section 2.2, we looked at quantitative variables, variables that take values that we can perform arithmetic operations on. We said using frequency distribution table and graphs like histogram and stem plot, we could summarize and present data for variables that are considered to be quantitative. In this section, we are going to look at summarizing data for variables using tables. I want to start by introducing you to what we call cross tabulation. Cross tables basically are summaries of data for two or more variables. We're looking at two or more variables that are presented in the form of a table form, and the best way to summarize these data is to use cross tabulation. In cross tabulation, we will also try to compare the relationship between the two variables. And please note that these variables can be either categorical variables or quantitative variables. Again, after that, we will look at what we call Simpson's paradox. Simpson's paradox are not important for the purpose of your midterms or finalisms, but they are good stuff to know, especially when you are discussing the influence of lurking variables in statistics. So let's go ahead. And I want us to start a two-way table by looking at what we have here. So here we're looking at different restaurants, the quality rating for the food they serve, and the meal price. In this raw data format, it's a bit difficult to actually be able to understand the different variables that are at play here. But we can actually transform this raw data set into a cross table form. Our cross table basically consists of two things: meal price and quality rating. This is called a 3 by 4 two-way table or a 3 by 4 cross table. Why do we call it 3 by 4? It's because we have 3 rows and 4 columns. And so this is basically a two-way table consisting of 3 rows and then 4 columns. Now, the number 42 here represent food from the restaurant that are the number of restaurants that serve their meals for 10 to 19 and are rated to be good. The number 64 here represent the number of restaurants who serve very good food between $20 and $29. The number 2 here represent the number of restaurants that serve good food between $30 and $39. Now, it's important to note that for every two-way table or cross tabulation, we have what we call the marginal totals. So this is called the marginal totals. And then over here too, we have marginal totals for the different columns. So if I'm to ask you, looking at this cross tabulation here of quality rating and meal price, how many restaurants serve food between $30 and $39? The answer will be 76. Now, another quick question. How many restaurants serve food that are considered to be excellent? And that will be the marginal total for 66 restaurants that were known to serve excellent food. Now, if we are to look at the cross table again, I can ask another question. How many restaurants sell excellent food between $30 and $39? And the answer will be 28. So I wanted you to spend some time on the cross tabulation here and then discuss the different cells and what they represent. And moving forward, I want us to talk about what we call Simpson's paradox. Simpson's paradox basically is a paradox in statistics where the reversal of a conclusion based on an aggregate data changes when the data becomes unaggregated. Simpson's paradox is what most of us will consider as never judge a book by its cover. What we see when the data is summarized into one or into a two-way table could be different when the data is actually given to us in detail in a three-way table. Let's take a look at a very simple example here to illustrate Simpson's paradox. When you are part of a jury, what you usually observe is whatever verdict the jury will bring out, the judge of the case decides to either uphold the verdict or reject the verdict. Now, for two judges who are in an experiment comparing the number and percentage of cases they upheld and the number and percentage of verdicts they reversed. And so it was known that Judge Luckett upholds 129 number of cases but reject 21 number of cases. It was also observed that Judge Kendall upholds 110 number of cases and reject 50 number of cases. Now, because these two judges has unequal number of cases they deal with, maybe it would be better if we look at this in terms of percentages. And so if a jury presents a case to Judge Luckett, he upholds it, which basically means he accepts or agrees with it 86% of the time, but Judge Kendall agrees with it 88% of the time. So based on this data here, most of us will agree, and if you're part of a jury, you will agree that Judge Kendall has a higher percentage of upholding cases than Judge Luckett. So everybody might end up saying Judge Kendall is the favorite. Now, this is what we call the aggregate data. If we are to unaggregate it, in this case, present what we consider to be a lurking variable, and a lurking variable in this case could be the type of court. We will observe that it's not all cases where Judge Kendall seems to be the favorite. In some cases, Judge Kendall is not the favorite. Let's take an example, municipal court. For municipal court, Judge Luckett upholds it 85% of the time and only reverses it 15% of the time, but Judge Kendall only upholds it 80% of the time. And so if the case is at a municipal court, Judge Luckett seems to be the favorite as opposed to Judge Kendall. And so take another look here. When the data is summarized in an aggregate form, everybody will say Judge Kendall has the highest rating for upholding cases. But when we go deeper and we split it, looking at the lurking variable, which is municipal court, we observe that Judge Luckett has a higher rating of 85% than Judge Kendall. And so Judge Luckett, therefore, seems to be the most liked judge when it comes to municipal cases or municipal court. And so you need to understand the influence of lurking variable. A lurking variable can actually give us an impression that may not be there. Let me give you another practical example of the influence of lurking variables. So a lot of people know that exercise increases fitness level, right? And so most of the times when you're asking to know how to be fit, the advice you usually get is exercise. Now that seems to tell us that there is a causal relationship between exercise and fitness level. If I exercise, my fitness level increases. But what if I'm to tell you that there is actually a lurking variable? And the lurking variable could be the diet. See, maybe diet is not part of our research. We are not interested in how diet affects the health or the fitness level. And so we are studying the relationship between number of exercise and fitness level. Now, because diet could be a problem, diet could be a lurking variable influencing the kind of results we get, right? So we do know that obviously there is a very strong relationship between exercise and fitness, right? But diet could be a lurking variable. It's not part of our research, but it can actually influence the fitness level of a person. So if every day I'm exercising, but my diet is not good, the diet could definitely affect my fitness level, and therefore diet could be a lurking or a hidden variable. Here, I want us to talk about relationship. In section 2.4, we are going to summarize data for two variables using graphs. See, in previous cases, we've been looking at using bar graph and pie chart or dot plot to summarize categorical variables. For quantitative variables, we've been looking at how we could summarize the data set or the distribution using a histogram and a stem plot. What if we want to establish or summarize the relationship between two variables? Now, again, please note that here we are only looking at the relationship between two quantitative variables. The best way to do that is what we call a scatter plot. Now, I'm going to quickly sketch a scatter plot so you could have a look at how scatter plots are usually represented. This is a very simple example of a scatter plot. How do we find a relationship between the scatter plot? So a scatter plot is basically used to establish relationship and to detect the strength of the relationship. For example, if we want to know the relationship between age and shoe size, we can talk to a couple of people and collect their ages and their shoe sizes and represent that on a scatter plot. Now, in business, there are so many different examples we could use. For instance, we could use a scatter plot to find a relationship between number of TV commercials and sales. Is there a positive relationship between TV commercials and sales? Do we hope to see the sales value increase as the number of TV commercials increases? Do people buy because there is a lot of commercials going on there? Another example, we could use scatterplot to find a relationship between exercising and fitness level. Is there a causal relationship? Is it a positive relationship? If we control the influence of the lurking variable, will we be able to see a strong relationship between exercise and fitness level? Now, another example, could we establish a relationship between future sales and promotions? So these are some of the things we could do with a scatter plot. Using a scatter plot to establish the kind of relationship that exists between two variables. Take a look at an example here. In this example, we are looking at two quantitative variables. Number of TV commercials, which will be our independent X variable, and our Y variable, which is the dependent variable, sales. Now, why do I call them independent and dependent variables? Independent variables because the values here is not dependent on anything. But we hope to see that the number of sales should have some level of dependency on the number of commercials. And so using these values here, let's try to plot it on a scatter plot. Now, every two values of x and y represent a single dot on a scatter plot. So this is what we have here. On the x independent or what we call the explanatory variable side, we have number of commercials. And then over here on the right, which is the dependent y response variable, we have sales. This data point here is represented by the value of X and its corresponding value of Y. And so over here, we see the data point for 41. And this data point here is represented by the relationship that exists between the X value of 1 and the Y value of 38. Now, based on this data plot, what do we see or what can we say? From our data plot, we can definitely say that there seems to be a positive relationship between number of commercials and sales. Now, why do we think it's a positive relationship between the two variables? Positive relationship because as the value of X increases on the X-axis, the value of Y also increases. So whenever you make a scatter plot or whenever you view a scatter plot and it follows in this direction, that is called a positive relationship. Now, another thing we could also say, apart from the fact that it's a positive relationship, has to do with the fact that it is linear. And so, number one, the relationship is positive. Number two, it is linear. Okay, so the data set, if we look at the distribution we see here, that we could draw a linear line between them, and that seems that it follows a linear form and the relationship is positive. Now the third thing we can also say is about the strength of the relationship. You see, when the data points are very close to our line, that tells us that the relationship is fairly strong. Now I say fairly strong because I'm not sure, I haven't used statistical tools to test how strong the relationship is. But in later chapters we will discuss that. And so it follows a linear pattern, it is positive and is fairly strong. Now the last thing we can talk about is other outliers. Now, the presence of an outlier could also affect the strength of the relationship. Now, over here, I don't really see an outlier. An outlier could be an observation that is just so far away from the distribution. Over here, this is an example of an outlier. All the data points are here, but this data point is so far off, we will consider it a possible outlier. Now let's continue with our description, and this time I want you to participate a little bit. This is a positive relationship. This is a no relationship. When it begins to flow from the top to down, we see a negative relationship. Now the rest of this section, I'm going to use it to discuss best practices. Not something you will be tested on your midterms or final exams, but good stuff to know. One best practice is if you want to compare the values of two different categories, or if you want to discuss how one category is performing better against the other, you could use a side-to-side bar graph. So a side-to-side bar graph basically is looking at multiple bar charts on the same display. And so we're looking at categorical data where we want to compare the values between two variables. Now, another thing we could also do is a stacked bar chart. A stacked bar chart basically is looking at each bar being stacked on top of the other. Again, don't spend too much time on it. These are not midterms worthy questions, but they are good stuff to understand. What are the advantages of a stacked bar chart? We can use them to evaluate or show the full scale of survey response, and we can also show how quantities change over time. Now, to close up this chapter, it's important to understand that some of the best practices in creating effective graphical tools Using data visualization, you could use a side-by-side bar chart if you want to compare two or more variables. And so the advice here is if we want to compare two or more bar chart, we could use a side-to-side bar chart. Now we could also make sure that our display has a clear title, and I think I already said it. Never ever forget to title your graphs. So if it's a bar chart, if it's a histogram, please make sure it always has a title. Now the other thing you want to do is you want to make sure it's simple. Don't be fancy and use 3D and stuff like that. Just be simple and create your graph. Now make sure your labels are labeled, your labels or your axes are labeled. You have colors that distinguish between the two axes clearly, right? And then use bar chart, pie chart, and dot chart for categorical values, but a line chart for quantitative values. Now, in most cases, when you go to the factory and we are looking at manufacturing country, they always have what you call a dashboard. A dashboard is looking at a set of visual displays that organizes and present data. We arrange our graphs in a format like this so that it will be easier for us to represent and compare the relationship between the x and y variables in a study. Okay, so this brings us to the end of the lecture note. Please spend some time and go over them. When we meet in class, we will solve some practice questions to help you prepare for the first midterm test. Thank you very much and have a wonderful rest of your day.